I'm Shuxiang Chao, talk about multi-agent blind computation without universal assistance. Please take it away.
Okay, thanks, John. And thanks everyone for coming to the talk today. I'm Shuxiang from Oxford Department of Physics. I'm currently a postdoc in the physics department. So this work was published late last year. It's my theory work about blind quantum computing using ZX calculus. Okay, so before we get started, let's dream about what will happen in the near future for quantum computing. So this is the figure that created by DALI-3 saying that what happened if we have a quantum machine sitting in our house. But obviously that's probably not going to be true because in reality, this is the hardware in our lab and it's a giant fridge. It's probably not going to be like shrink into a small chassis and you can put it in your house. So in that case, the best way to implement to do the quantum computing is probably have to do the Claude style. That is, let's say the Alex wants to run some quantum algorithms. So he prepared his, the algorithm here, we write it as the ZX diagram. And then for Bob, who actually owns the quantum computer, then Alex can send the algorithm to Bob and get the answer. However, let's say if Bob is in fact not not very polite, and he could actually steal everything Alex upload to his quantum computer, so Alex will not be happy about it. To resolve this problem, let's say, imagine a case that we're not using only one quantum computer, but we might have more than one quantum machine. So now Alex prepares his quantum algorithm and split it into different pieces and send it to, let's say, Bob and Chris. And then we will wish Bob and Chris may have some shared bell pairs to implement the algorithm, pre-shared bell pairs, so they do not communicate with each other during the execution of the algorithm. So now Bob will be very confused, and the limited information he obtained will not be able to infer what Alex had. Okay, so the concept was mentioned above, and I'd like to recap the measurement-based quantum computation approach, which is the base, the foundation of this new method. So let's say the measurement-based quantum computer is by saying you prepare a resource state, and then you implement a series of measurements. And after each measurement, you can implement a correction on the remaining of the resource state. Afterwards, the outcome, the output of the resource state will be exactly the same as if you executed the circuit. So the ZX calculus has a correspondence to the measurement-based quantum computing. And here I would like to recapture the graph-like ZX diagrams. So the graph-like ZX, let's say the original circuit, the ZX, we can directly rewrite our quantum circuit into a ZX diagram as shown in figure A. And then we can rewrite it into diagram B, shown here, where this is an example of the graph-like ZX diagram. So all the spiders are only these spiders, and they are connected only via the Hartman wires. And there is no parallel Hartman wires or self-loops, and every input or output is connected to the Z spider, and only the Z spider is connected to the most one input or output. So to implement measurement-based quantum computing, you can first consider about pushing the pi spiders. So this is the rules, like you change a sign of your green spider, then it actually emits four red pi spiders on its wires. And for measurement-based quantum, for the correction step of the measurement-based quantum computing, you can consider your graph-like ZX diagram. Each of the node is a qubit, and you can grow an extra leg on each of these qubits. And then when you perform a measurement on each of the qubits, you may find your measurement outcome is 1. Then that means you plug a pi spider to that qubit. And then because the original algorithm, you do not wish to have this pi spider, you can apply these pi rules to push these spiders away to these unmeasured qubits and implement the correction. So, however, not arbitrary diagrams can be corrected with this approach. So the pattern must be at least admit a so-called polyflow to allow this method work. So what is polyflow? So on the left is the official definition of the polyflow, but I will keep it short using my own understanding to interpret it. So the first statement of polyflow is that once you measured a unwanted pi phase, then you can in fact find a stabilizer on your graph. So the stabilizer is like, in fact, instead of correcting one qubit, you might be able to correct multiple qubits to recover your state. And then once you find that stabilizer, you need to make sure that the correction needs to happen on those qubits that has not been measured yet. Because once you measure, you cannot change its state anymore. And then except if you are actually trying to flip a sign of a 0 phase or pi phase spider. For that case, even if your pi red pi goes across that spider, because it's 0 or pi, then it goes to 0 again, or minus pi, which is equivalent to pi, then nothing will change. So basically, this is the rules that are required of the polyflow. So in this work, I propose a new type of ZX diagram. It's called semi-graph-like diagram. So it's like the graph diagram, except you remove the restriction that your nodes must be, your spiders must be connected via the Hartman wires. So in that case, you allow the diagram to be connected with the regular wire, and therefore you could always recover a graph-like diagram with only the fuse rule. Like you can remove all these regular wires and fuse all these spiders and recover a graph-like ZX diagram. So why would we be interested about the semi-graph-like diagram? That is because if you think about the phases of a semi-graph-like diagram, if let's say, for example, here I have 4 spiders, they are all connected via the regular edge. And then when I measure it, I would obtain 4 different phases plug into each of these spiders. And then equivalently, you will get, it is equivalent to just measure its corresponding graph-like diagram. So it corresponds to one node. And then the phase of that one node will be the sum of the phase of these 4 nodes. So before deep into detail of my protocol, I would like to first review the previous universal blind quantum computing protocol, which is the standard in this area. And this protocol requires to create a very complicated break-word cluster state. And this is the way you can translate your circuit diagram, circuit model into the measurement-based model on and implement it on the break-word cluster state. And then the universal blind quantum computing protocol has two types. So the first type is you have a quantum agent, a quantum agent and a quantum client. While your quantum client may have very limited resources, say you have only 1 qubit. And then your agent will prepare this break-word cluster state, and your client can either teleport the prepared face to your agent and allow your agent to measure, or the agent can teleport the state back to client and let the client measure. So alternatively, the universal blind quantum computing protocol has a multi-agent version. So in this version, your client can be fully classical, but you would require another agent B to implement what's supposed to be done by the semi-classical agent. So this is the previous work. So in our proposal, instead of creating the very complicated cluster state, here I propose to use ZX calculus to rewrite the algorithm and break its connectivity, the phase and outcomes onto different agents. And if for each of the agents, it will have only very limited information, and therefore it will not be able to infer what has happened, what is requested by the client. So now please allow me to walk you through the protocol here to implement the blind quantum computing. So the first step in our protocol is to rewrite the circuit into a ZX diagram, and then and then you rewrite it into a graph-like ZX diagram. So once you get the graph-like ZX diagram, you can split each spider into two spiders connected by a regular edge. So these new spiders, the face of these two new spiders should sum up to be the face of the original spider, but each of them may have a random face. And then we can assign the blocks to the diagram, where the blocks is defined by the distance to the output qubits. So to the very output qubits, and then each of the blocks will be assigned to different agent for execution afterwards. A specific note is that we want to make the two spiders split from the previous step in the different blocks. So therefore, each block, so the agent possess one block will not be able to recover the original face of this spider. So in the next step, we can implement the connectivity obfuscation. So by this, we mean that within each block, you may have some hard-marked wires, but we would like to hide these hard-marked wires from the agent. So therefore, we make them wires that connects between blocks. This can always be done because in the previous step, we have just splitted the spider, and they are connected in the regular wire, and these two spiders belongs to different blocks. So in the next step, we implement the connectivity obfuscation. So what it means is for all these wires connecting between blocks, we grow two more spiders and then connect and replace the direct wire with these two black spiders plus 3 hard-marked wire. So this rewrite rules is in fact easy to prove equivalent to the original the X diagram. However, the difficulty here is in fact we need to show that this rewrite rule also preserves the Pauli flow, which makes which keeps these rewrote diagram still executable on a measurement-based quantum device. And I would like to thank Professor Miriam Beckens and her student Tommy for proving that this rewrite rule in fact still preserves the Pauli flow. And I believe they are going to discuss about this exact proof in the following week. So if you are interested, please come to their talk in the next week. Okay, so now the obfuscated diagrams are done. So let's look at how we can execute them on a quantum hardware. So at the very first step, we prepare the pre-shared Bell pairs. We assume they already shared between the agents. So in this particular configuration, we say the very left and the very right blocks belongs to one agent, and the middle block belongs to the other agent. And the next step is we would like to implement the regular wires from the pre-shared Bell pairs. And the way of doing that is by applying hard-mark gates on some particular spiders. And we can, in the paper, we show that using the rules I've shown on here, you can in fact implement this extraction without exposing which edge is regular edge and which edge are hard-marked edge. So the agent will not be able to know. So in the following step, we reconstruct the obfuscated graph. So this is done by implement some entangling gates within each agent. So note that while each agent know that there are a few wires connected to one spider, they do not know where is the other end of this wire. So this is the method we kept the entire ZX diagram safe. Okay, so now let's say we run the measurement followed by following the Pauli flow. So in this particular setup, let's say we measured a pi spider at V2, but we in fact wish V2 has no face. So now we plug in a pi face. So then we can based on the Pauli flow, we can look at the correction set of V2, which is V3, V5, and V7, and then we implement the correction by following the Pauli flow by following the Pauli flow, and then we flip in the end we flip the face of V3 V5, and we got an extra pi spider after V5, which we can classically handle afterwards. So here I would like to introduce an extra patch to obfuscate the resource requirement. That is, so in the previous step, you may notice that each agent will still be able to know like how many wires are attached to a particular spider. So here we can use these rewrite rules to grow extra spiders that attach to a spider, which hides the actual resources required to implement the algorithm. Again, this rule also preserves the Pauli flow and has been proven by Professor Miriam Beckens, and they will talk about this proof in the next week. Okay, so now let's discuss about the secureness. So what would an agent know in order to run the algorithms? So here I listed 4 components. The first is the agent will know like it applies some it will know that how many bell pairs it have, and also what is needs to be done to to apply to the spiders of these bell pairs. So for this for the bell pairs in the paper, I've shown that even if you apply some hard-marked gate on these bell pairs, the agent is not able to tell if that bell pair carries a hard-marked edge or a regular edge. So the second is the agent does not know where to create the entanglement between qubit. So the agent knows where to create the entanglement between qubits within each block, but they do not know what will happen between the blocks. So the information of the bell pair used is independent from the algorithms. And then the agent will, based on this, the agent, although they know the number of the bell pairs, but it may only know the maximum number of entanglement performed on the same qubit. So it's not the exact number, but it's the maximum number that could have been performed on the qubit. So the third information that agent know is the phase of the measurement. However, because of the phase obfuscation step, the measurement phase are uniformly random. So in the end, the agent will also know the outcome of the phase. So here we applies the same approach as the universal blind quantum computing protocol, where you randomly add a pi phase to your spider before measurement, and then once you get the measurement outcome, you can classically cancel that pi phase and recover the original distribution. But that classical information will only be possessed by the client instead of the agent. So the measurement outcome will be uniform for all the agents. So so how do we quantify the secureness? So in this work, we mentioned two approach. The first one is developed in the very first paper in the universal blind quantum computing, where it tries to find what is dependent to the algorithm and what is not. And after analysis, we find our protocol will maximally reveal the following information. The first is the maximum entanglement of a specific qubit, as I just mentioned. It's like how many wires, the maximum wires can attach to a specific spider. And the second is the number of qubits within each block, and also the number of blocks. So compared to the universal blind quantum computing protocol, we have a extra leakage, that is the maximum entanglement number of qubits. So the first one. However, because we have that obfuscation protocol, so we can always add more dummy spiders attached to the spiders. So we consider, even if we leak this information, it will not hinder the secureness of our protocol. Another way to quantify the secureness is shown here. Basically, this protocol is this private definition is by saying that your blind quantum computing channel will implement some quantum map, but it implements map. Maybe it only implements map jointly by having the other quantum channel, like the information coming in or afterwards, are making sense. So if this channel is dependent to its environment, then it's less secure. However, if it's completely ignorant to the environment, then it is secure. So in this protocol, so in this definition, it defines a simulator called SI. So basically, your agent, let's say this is AI, it might be communicating with other agents that actually generating some meaningful data for meaningful for meaningful computation, or it could have been just connecting to some random stuff by this simulator. And we want to know that if the agent can tell it is running something meaningful or it's running something completely irrelevant. So if it could not tell, then we will be able to say this protocol is secure. So in the definition, the secureness is quantified by the diagonal distance of these two channels. And in our paper, we mentioned that. Sorry, I just disappeared. So in our paper, we mentioned that we use the Treja-Minkowski state, which is in fact the entanglements, the measurement-based, the cluster state prepared, reconstructed by each agent. We show that these states are always identical. So therefore, the quantum map implemented by the measurement-based protocol are also identical. So therefore, our protocol is zero private, and the agent will not be able to tell if it is doing meaningful calculation or it actually connects to some random simulator. So in the end, I would like to highlight the advantage of our protocol. So why we're thinking about this approach. So we find that using our approach, we significantly reduced we call it external entanglement number. It's like the number of shared bell pairs you would need to implement the algorithm. So with the with either single qubit or single agent or multi-agent universal blind quantum computing, you would always need a scale of 4DW plus W. While for our proposal, you would only require 1DW plus T, while T is like the number of 2-qubit gates you would involve. So in that case, if your two qubit gate, so if you do not have a very complicated connection diagram, then our protocol will be much more efficient than the universal resource efficient than the universal blind quantum computing protocol proposed. So in conclusion, I would like to say that we managed to use the ZX calculus to find a blind quantum computing protocol. And compared to the previous proposals, the new protocol requires less resources. That's the takeaway message. And for that, I would like to thank my colleagues at the physics department and Leah and John at the computer science department, and Professor Miriam Backens at Birmingham for her kind support on providing the proofs. Yeah, and I'm ready for any questions.
All right, thank you very much, Shuxiang.
Yeah, thanks.
Yeah, are there any questions in the audience? Yeah, so I have a question. Although I did have to change my train at some point, so I did miss some of your presentation. So apologies if this was already covered. I was just wondering in terms of security guarantees, whether also your protocol is stronger than previous ones. Because if I recall from what these previous protocols were, you were sort of shaping the actual shape of the protocol, like it was like unclear. like how qubits are traveling, but in your protocol, it sort of seems that even the angles and the connections themselves are obfuscated. So I'm wondering if there's like if you could sort of say that there is a stronger security assumption that you have in your protocol.
I mean, you need a stronger assumption, or if the protocol is more secure than the previous one.
Yeah, maybe more secure is the right term. Yeah.
In fact, I believe our protocol is slightly less secure, as I mentioned here. So in the universal quantum computing protocol, that protocol leaks the number of blocks and the number of qubits. So this unbeaten, so the previous one leaks that, but they do not leak this message, the maximum degree of VI. However, because we have so we leak this extra information, so which makes it slightly less secure. However, we show that with the previous approach, like we can always add add dummy spiders to yours to these existing spiders without changing the outcome of your diagram. So therefore, they can only infer the maximum entanglement to the qubit VI, but not the exact entanglement. So therefore, we believe leaking this information will not hinder the secureness of this protocol.
And I can sort of see if you have these intermediate blocks that they can't really tell how far along they are in the computation. But for the first block and maybe the second block, like how does it work with sort of the input state where they're because they can tell that they're the input state, right?
Yeah. So in this example, we show that the input state is somehow teleported to the first agent. But if that teleportation happens, it basically means that your agent is connecting to another agent, while the other agent is also not revealing anything to the very first agent. So it's like the very first agent is no longer the first agent. So as the input. If we're not having a quantum input, then this is just a pure ZX diagram. And therefore, so let me find, so for example, here, then if this becomes a pure ZX diagram, then in fact, the Bell state on the left and the Bell state on the right is exactly the same. So they will not be able to know that where the information is teleported from and where it's going to go. So therefore, even if it's at the very first agent, it is the very first agent, it will not be different from the agent in the middle.
Okay. So it's maybe a different question, but is it also secure, or can you verify that these blocks are not malicious, that they are actually executing the thing that you are asking them to execute?
Well, I didn't include it in the talk, but I discussed it in a paper that this protocol is compatible with almost all the proposed verification approach. Like you can implement traps in the diagrams to make sure that the information so the agent is behaving correctly. However, because they are compatible, so it's not the key of this protocol, but we do discuss that they are compatible.
I have a couple more questions, maybe other people in the audience, if there's any comments or questions. All right, so I've been learning a little bit of the cryptography and the language they use over the last year. And I know there's this thing about like multi-party secrets and say like you have like K different parties and that it can be secure if at most say L people collude together. that like as long as fewer than L people collude, there is no way they don't have any information about the thing executed. But as soon as there's like L of them, then they can reveal the secret, for instance. I was wondering like what the case is here. Like if I have say 3 parties and 2 of them collude, like do they get additional information?
So for this protocol, they will be able to get information. So here we assumes that the adjacent blocks are so the agents carries information in the adjacent blocks are non-collusive. So if they are collusive, then you will be able to recover some of the information by merging this by simplifying this obfuscated diagram.
Okay, so then they get some information, but not necessarily all of it. Like it's still
but not exactly. So if we manage to have a lot of agents, then it's like you shattered the information into, say, hundreds of pieces that maybe 2% can expose to collusive agent.